Trigonometric equations, chapter 7, section 3. So let's start out with checking whether a given number is a solution of a trigonometric function. It's always good to start at that point, right? Rather than trying to solve something, check and see if a value is a solution for it, because that's just plugging it in, right? So checking whether a given number is a solution of a trigonometric function, determine whether pi over 3 is a solution to 2 cosine theta minus 1 equal to 0. So all we have to do is substitute pi over 3 for theta. So we get 2 times cosine pi over 3 minus 1, which is equal to 2 times the cosine of pi over 3 is 1/2. So 2 times 1/2 minus 1. 2 times 1/2 is 1. 1 minus 1 is 0. So yes, pi over 3 is a solution. If we had plugged in something else, pi over 4, then we would find that pi over 4 is not a solution, because cosine of pi over 4 is, well, pi over 4 is 40 degrees. So that would be square root of 2 over 2. 2 times the square root of 2 over 2 is 2 square root of 2 over 2, or so square root of 2 minus 1 is not equal to 0. So I had to wing that and do that in my head. So now that we've plugged in to see, is this a solution? How do we find all the solutions of a trigonometric equation? So solve the equation tangent theta is equal to the square root of 3 and give a general equation for all the solutions. Well, we know the period of the tangent function is pi, which means that if we find a solution for it, it's going to replicate every pi. So add pi to it and we're going to get another solution. In the interval from 0 to pi, tangent of theta equal to the square root of 3 is true when theta is equal to pi over 3. And you can get that from the unit circle or from drawing your triangles out. You know, the 1 square root of 2 or the 1 square root of 3 triangles. So you come up with theta is equal to pi over 3. So we know that's in that first interval, but then we also know that it's going to replicate every pi, every period after that. So we can say the general equation for all the solutions is that theta is equal to pi over 3 plus k times pi, where k is an integer. So that means what if k is 1, we're adding pi to it once. If k is 2, we're adding pi twice. If k is -1, we're subtracting pi. So that's moving it pi either right or left. So it gives us all of the possible solutions. What about solving a linear trigonometric equation? Now, that may seem a little strange to say that a linear trigonometric equation, by definition, a trigonometric function is sinusoidal, which is not a line. So what we're talking about here is solve the equation 2 sine theta minus the square root of 3. Now, if you were to substitute x for sine of theta, you would see you have 2x minus the square root of 3. Y equals mx plus b, right? So that would be a standard linear equation. And that's what we mean when we're talking about a linear trigonometric equation, is basically it's written in a way that if you were to substitute in a variable for the function sine of theta, that you would have a linear function. So we're solving 2 times the sine of theta minus the square root of 3 is equal to 0, where theta is between 0 and 2 pi. So basically, what would be considered 1 full period. So we can look at that and say, well, if we're trying to solve for theta, we're going to get it by itself. So we add square root of 3 to both sides, giving us 2 sine theta is equal to the square root of 3. We then divide both sides by 2. So sine of theta is equal to the square root of 3 over 2. And now here's where that inverse function comes in. If we want to find theta, we take the inverse sine of both sides. The inverse sine of the sine function just leaves us with theta. And the inverse sine of the square root of 3 over 2 gives us pi over 3. We know that sine is positive in the first quadrant and the second quadrant. So it is not only pi over 3, but it is also 2 pi over 3. Because remember, 180 degrees is pi. Pi minus pi over 3 gives you 2 pi over 3. So first and second quadrants. So that's how we solve a linear trigonometric equation. Well, that was fun. What about a quadratic trigonometric equation? We can't just leave it at a linear, right? We like quadratics. So let's say we want to solve the equation 2 cosine squared theta plus 3 cosine theta plus 1 is equal to 0 on the interval from 0 to 2 pi. Well, we can treat the cosine theta like the variable x in a quadratic and factor. So we can look at that and say, well, isn't that the same as saying, or we can substitute, it's the same as saying 2x squared plus 3x plus 1, where x is equal to cosine theta, right? So we can look at that, and that's easy for us to factor, and we see that it would be 2x plus 1 times x plus 1, or 2 cosine theta plus 1 times cosine theta plus 1 is equal to 0. And now we can use the zero product property to solve for theta, right? 2 cosine theta plus 1 is equal to 0. Cosine theta plus 1 is equal to 0. So 2 cosine theta plus 1 equal to 0. If we subtract 1 from both sides and then divide by 2, we get cosine theta is equal to negative 1/2. And then if we take the inverse cosine of negative 1/2, we get 2 pi over 3 for theta. And then cosine is negative in the second and third quadrants. So we can take that 2 pi over 3 is actually pi over 3 less than pi. So we can add that pi over 3 to pi and we get 4 pi over 3. Remember, always in reference to the x-axis, which in radians, that's pi or 2 pi or 0. In degrees, it's 180 degrees or 0 degrees or 360 degrees. So that gave us for the first factor. The second factor is cosine theta plus 1. So we can say cosine theta is equal to negative 1, subtracting 1 from both sides. And then the inverse cosine of negative 1 is 3 pi over 2. And there's only one spot where cosine theta is equal to negative 1, and that's 3 pi over 2, because that's a quadrantal angle. So it's the similar process. We're basically taking a quadratic function and then we're breaking it down into linear functions and solving from there. Now, could we make this more complicated and take it to a point where you would have to use the quadratic formula to solve for these? We could, but that would just plain be mean. Okay, so solving a trigonometric equation using identities. What if I want to solve the equation 2 sine squared theta equal to 2 plus cosine theta for theta equal from 0 to 2 pi? Well, now we're going to bring in some other things. I said it could get more complicated. Well, what we can do here is we can say, well, wait a second. 2 sine squared theta. Well, sine squared theta, if I use a Pythagorean identity, remember sine squared theta plus cosine squared theta is equal to 1. So if I solve that for sine squared theta, I find out that sine squared theta is equal to 1 minus cosine squared theta. So all I did was I solved our standard trigonometric Pythagorean identity of sine squared theta plus cosine squared theta is equal to 1. I just solved that for sine squared theta and got 1 minus cosine squared theta. So now I have 2 times the quantity 1 minus cosine squared theta is equal to 2 plus cosine theta. Well, now that I've got that, I can distribute through my 2, and I get 2 times 1 is 2, and 2 times cosine squared theta is 2 cosine squared theta. So now I have 2 minus 2 cosine squared theta plus 2, is equal to 2 plus cosine theta. Well, now I'm trying to get theta by itself, so I'm going to move the 2 over to the other side. So I'm going to subtract 2 from both sides, and I want to get cosine together, so I'm going to subtract cosine theta from both sides. So by doing that, subtracting the 2 from both sides cancels out the 2's on both sides, so leaving me with negative 2 cosine squared theta, and then subtracting cosine theta from both sides brings in minus cosine theta is equal to 0. Now, you're probably like me and you don't like that negative sign in front of everything, so we can divide through by -1, leaving us with 2 cosine squared theta plus cosine theta is equal to 0. And then I look and then I say, wait a second, I can factor that. I've got a common factor of cosine theta. So if I factor that out, I have cosine theta times 2 cosine theta plus 1 is equal to 0. Now I have 2 linear functions. So cosine theta, I can set cosine theta equal to 0. And I can set cosine theta equal to -1/2. Where did I get that -1/2? 2 cosine theta plus 1 is equal to 0. So 2 cosine theta is equal to -1. So cosine theta is equal to -1/2. So I just solved for cosine theta in that second factor. So I get those two values. So cosine theta equal to 0. If I take the inverse cosine of 0, I get pi over 2, and then cosine is positive in the first and fourth quadrants. Sorry, not positive, we're 0. So when is cosine equal to 0? It's equal to 0 at pi over 2 and 3 pi over 2. Those are quadrantal angles I misstated as I started. And then cosine theta is equal to -1/2. The inverse cosine of -1/2 gives me 2 pi over 3, and it also gives me 4 pi over 3 because cosine is negative in the second and third quadrants. So again, that's 3 pi over 3 minus pi over 3 and 3 pi over 3 plus pi over 3 to give me those values. So using trigonometric equation and identities to solve a trigonometric equation. And remember, when we do this, we need to make sure that we include all of the possible solutions. We're always going to get the reference angle. We then have to look at the other quadrants where we could get that same value and include that angle also.